Section 4.3, Increasing and Decreasing Functions and the First Derivative Test. In this section, that is an application of derivatives, we are going to study how functions increase and decrease on certain intervals. And then we'll look at the first derivative test, which allows us to declare whether a certain value is a maximum or a minimum. So first, this theorem, which we could really just think about it and figure out these missing elements. You don't have to copy them and think of them as a definition. It's something you can think about and realize by yourself. The first one says that if f prime of x is greater than 0, then that means the function is increasing. We have talked about that a lot. If the derivative is positive, the function is increasing, and vice versa. If the function is increasing, then the derivative is positive. Likewise, if f prime of x is less than 0, that means f is decreasing. And vice versa, if f is decreasing, the derivative is negative. And finally, there's the case that is squeezed in between. If f prime of x equals 0, then on that interval, f is constant. So it could happen that you have a whole interval from a to b where the derivative is 0, then that would mean the function is horizontal, constant on that interval. If f prime of x equals 0 at one specific point, this is something we will discuss further in this section as well. So let's see how we can use that to decide intervals on which a function is increasing and decreasing. Think about how useful it can be if we need to sketch complicated functions. If we could always know, oh, I know it's going up between 0 and 5, and I know it's going down between 5 and 8, for example. So in this exercise, f of x equals x cubed minus 4x, and we are going to try to find intervals where it's increasing and decreasing. This is a cubic polynomial, so you can have a vague idea of what it looks like. It may go up and then down and then up again, or down, up, down, or it might just go up all the time, or it may have a saddle point. That's what we will find out. The strategy to do that is, of course, to look for the first derivative and then the critical values. The first derivative is easy, and then finding the critical values, we are looking for where f prime of x equals 0 and where f prime of x is undefined. So where could this be equal to 0 when x is plus or minus the square root of 4 over 3? Where could that be undefined? Never. A polynomial is always defined, and all its derivatives are always defined as well. So it's never undefined when f is a polynomial. Why did we want to find the critical values? Well, if you think of a function, let me just draw a random function, quite complicated. If we want to know on what intervals a function is increasing and decreasing, it is always going to be sliced by places where the derivative is 0 or undefined. This function is increasing until here, where the derivative is 0. Then it looks like it's decreasing until here, where the derivative is 0. Then it's increasing until here, where the derivative is undefined. Then it's decreasing until here, where the derivative is 0, and so on and so on. So every time there is a switch between increasing and decreasing, it's because we've reached a point where either f prime is 0 or f prime is undefined. You can't find any other situation. If you imagine, for example, a vertical asymptote, that's f prime of x is undefined. And that could be a place where the function is increasing before the asymptote and decreasing after the asymptote. So these are the places where there's a potential for a switch between increasing and decreasing. I say potential for a switch because we could have a function that goes up, then f prime is 0, and then it goes up again. So here we would find that as a critical point if f prime of x was equal to 0. And it doesn't have to switch between increasing and decreasing. Here it's increasing 0 and increasing again. So once we've found the critical values, and in this example there are only two, x equals negative square root of 4 over 3 and x equals positive square root of 4 over 3, it allows us, in a way, if you look at this sketch here, to slice the function into three zones. It's like if I had an A4 paper and then I just cut the page here and I cut the page here as well. And I know that in this region here, the function will either be increasing or decreasing. In that region here, between the two cuts, the function will be either increasing or decreasing, and in the third region as well. It is not possible that the function increasing and then decreases in one of these intervals that I've defined, because if it was increasing and then decreasing, I would have found the point where it changes. That point where it changes would have been one of the critical values that I would have found. So since I didn't find one, it means it's either just increasing the whole time or decreasing the whole time. So rather than looking at an entire Cartesian plane like this and slicing the page, we usually just draw a number line. What you see here is a simplified version of that here, where we in fact only sketch the x-axis. Now to realize whether f is going to be increasing or decreasing in each of these zones, all we need to do is to pick one value that is in the interval. So between negative square root of 4 over 3 and positive square root of 4 over 3, the easiest number we can pick is x equals 0. But any number in the interval would do. So if I choose x equals 0 and I plug it in f prime, I get f prime equals negative 4. So f prime is negative, which explains why there's a minus sign here. I add this negative sign to say f prime is negative between here and there. So for the graph, it means it would go down. I don't know if it goes down from up here like this, or if it goes down from down here. I don't know if it goes down a lot or not a lot, but I know it has to go down from from x equals negative square root of 4 over 3 to x equals positive square root of 4 over 3. Then I have two more zones. I started in the middle because it was the easiest, but I have a zone here and a zone there. And I have lots of choices. I just need to pick one point, and that point is going to define the entire interval, whether it's increasing or decreasing. What I like to do, let's start with the positive one. So I need to choose a point x that is greater than the square root of 4 over 3. I'm not quite sure what square root of 4 over 3 is, but what I typically do is I choose just a very big number. I don't even really need to choose it, but I can say, what happens if x equals 1000? I'm definitely going to be in the correct zone, and I can see that if x is equal to 1000, this is going to be huge, and minus 4 will have no impact. So f prime is definitely going to be positive. So I put a plus here, and now I know that the function goes down, and then it goes up. Finally, I need to figure out how to find this plus here, and this time I need a number less than negative square root of 4 over 3, so how about negative 1000? And you'll see with the x square, it's going to become a huge positive value, minus 4. That minus 4 is ridiculously small compared to the millions we're getting, so the result is f prime is positive. So now I've built my entire number line. F prime is positive, negative, positive. It's nice to put f prime here to indicate what the sign represents. A number line in AP Calc AB never counts for any points. It's a tool that we use, but it doesn't count as an answer. So we always need to spell out the answer, which is represented here, and we're going to go in order. Because f prime is positive, it means f is increasing. So we write f is increasing from negative infinity to negative square root of 4 over 3 because f prime of x is positive. In between here, we can write f is decreasing on the interval from negative square root of 4 over 3 to positive square root of 4 over 3 because f prime of x is negative. And then again, same here. So each of these signs on this number line corresponds to one of these lines here. So now we know that whatever the graph does, it's going, wherever the graph is, it might be high up here, it might be low down here, but what we know is it's going up until it reaches this, this cut, this critical value, and then it goes down until this critical value, and then it goes up again. First, derivative test. If a function is continuous on an interval, then if f prime changes from negative to positive at a certain value c, then f has a relative minimum. This relative minimum might also be the absolute minimum. We don't know. We know that it's at least a relative minimum. Why is that? So we have a situation here that's represented. The f prime changes from negative to positive at x equals square root of 4 over 3. So we are in case A here. F prime changes from negative to positive at square root of 4 over 3. Well, if you remember how I kind of sketched the graph, it might look like this, and then like that, and then like this. So what's special about x equals square root of 4 over 3? We have a minimum, because it was going down and then it's going up. So it has to be a minimum. B is the same. If f prime changes from positive to negative, then f has a relative maximum, which could even be the absolute maximum. That's the case we had at negative square root of 4 over 3. F prime was positive, and then f prime is negative, so I must have gone through a maximum. So these are sketches that represent the simplified situation. And finally, if f prime is positive or negative on both sides of c, then f of c is neither a relative min nor a relative max. This is an example where f prime is positive, then 0, then positive again. So it's not a max, it's not a min. That is the first derivative test. Let's apply. Find the relative extrema of this function f using the first derivative test. So we are going to want to find where and what kind of extreme values we have for this function. All we need to declare is if it's a relative min or if it's a relative max. To do that, we're going to use very similar tools as to finding whether a function is increasing and decreasing. It's pretty much just one extra step. So that's a good way to review. The first thing we do is we want to find the first derivative. So f prime of x, here there is a chain rule, so it's 2 over 3 x squared minus 4 to the power of negative 1/3 times the inside derivative. I simplify this a little bit, clean it up, because this is not the end of the question, so I probably am going to use this expression, and the cleaner it is, the easier the next steps are going to be. I search for the critical values, so can f prime of x ever be 0? That happens when the numerator is 0, so x equals 0. And then is f prime ever undefined? That happens when the denominator is 0. And so we can see that when x is plus or minus 2, we will have a cube root of 0, so we will divide by 0. When this is done, we can slice the graph, or rather just draw a number line where we place all our critical values and make sure you place them in order. So negative 2, 0, 2, because this is the order. And then for each interval, all I need is to pick one value, and we know that that value will represent the entire interval in terms of increasing or decreasing. So the easiest here for me is to choose a value between 0 and 2, and 1 is the best choice probably. So what happens if we pick x equals 1? The derivative is going to be 4 divided by 3 times 1 minus 4. So we have a cube root of a negative number. Cube roots of negative numbers exist. It remains negative. And so rather than having to calculate everything, we see that the numerator is positive, it's 4, and the denominator is negative. So the overall answer is going to be negative. So I can put a minus here. It means f prime is negative. It means f is decreasing. Then I'm going to pick this one here. Here I'm going to choose negative 1. x equals -1, it's going to be negative divided by negative. So that means f prime is going to be positive. What about here? I need to choose a number bigger than 2. Maybe I can choose just 10. 10 is big enough. I'll get 40 divided by, this is clearly positive because it's a cube root of 96. So I have positive over positive, which is positive. Lastly, I need a number less than -2 to represent all the values of x that are in the interval from -infinity to -2. I'll choose -10. I get -40, so negative at the numerator. And here, -10 squared is positive. -4, it's going to be 96. If I chose x equals -10. So I have negative over positive, which is negative. So the function has a derivative that is negative, then positive, then negative, then positive. So rather than writing intervals, we could have done it. That's what we did in the previous example. It would have been f decreases from -infinity to -2, then f increases from -2 to 0, then f decreases from 0 to 2, then f increases from 2 to infinity. We are only interested in what the critical points are. So if the function f decreases and then increases, we have a minimum, and if the function increases and then decreases, we have a maximum. So, and then in the end, it decreases and increases again, so we have another minimum. So the minima are at x equals -2 and x equals 2, and the maximum is at x equals 0. For all of these, if we want to know the value of the minimum and the maxima, or the minima and the maximum, we can plug the values of x in the function, and it will give us the value. So if f equals -2, f equals 0, right? -2 squared is 4 minus 4, so it's going to be 0. Same with f equals 2. And finally, for the maximum is at x equals 0. So if I plug this in, I get 0 minus 4 squared, which is 16, and then cube root, so cube root of 16. We are able to do this entire exercise without a graph, but now that we've finished the exercise, it could be a little illuminating to see what the graph actually looked like. And this is it. If you type it on your TI Nspire, it kind of bounces. These are the two places where f prime was undefined. It makes sense. It's sharp turns. This is where f prime was equal to 0. It's a horizontal tangent line. So you can see the graph is decreasing, increasing, decreasing, and increasing again, exactly like we had calculated. Thank you. That's all for section 4.3.